Using the Solid Edge startup screen will open an existing assembly. Notice the options on the dialog box. Many of these options are geared towards handling massive assemblies like hiding all components for super fast opens or opening a specific design area with a zone or configuration. This assembly already contains the 2D layout that we previously opened from AutoCAD as an assembly sketch. We've also added a lot of virtual components. These components are placeholders for future parts and assemblies and enables us to quickly build an entire assembly structure without initially creating documents on disk. Let's take a look at how this works. If you're working on a familiar design, more often than not you'll have a good idea of what needs to go into the assembly. So why not capture this up front? Think about this. If you were asked to build a bicycle, you'd probably list most if not all the components. That's what virtual components is all about, a tool for jotting down your ideas quickly. We can enter our own part name or choose from a library of components. This library can be categorized by document type, such as parts, sheet metal components, and assemblies. Watch as we add more assemblies. If the structure is not quite the way we want it to look, we can simply drag and drop components to arrange the assembly tree exactly as we want it to appear in production. This tree actually represents our bill of materials. Working with virtual components is ideal during the initial or conceptual phase of an assembly design. We can add as many components as we need, and remember that these will at some time become real parts. The key here is being able to organize our structure however we want. We can also add real parts and assemblies to our design. While you may expect to see the physical 3D components when we're done, Solid Edge has some built-in optimizations that we'll look at a little later. Now the assembly tree lists the new virtual components and they are in the right spot. Keep in mind at this point no additional files have been created. We'll do this later. Thinking about the power here, we have no files to manage and performance will be optimal. This is just the thing needed for working with massive assemblies. Now that both the structure and the layout are complete, a natural next step is to tie the 2D sketch components to the virtual components. We call this unique workflow 0D. We'll take a look at this entire process by drawing some elements, adding some dimensions, and then assigning the geometry to a virtual component. If you remember the easy-to-use drawing tools we used back in 2D, those same commands are available in 3D. We can quickly add a couple of dimensions using the Smart Dimension tool to precisely locate the profile relative to the plant walls. This component we just drew is actually going to be a subassembly of the boiler. With our 0D workflow, we can easily assign the rectangular sketch to the boiler frame assembly. Now we'll quickly create more geometry to represent other components inside the boiler frame. Notice that by not constraining the sketch to a particular dimension, we can easily drag the elements around to achieve the shape and position that we want. The internal components can be assigned to other virtual components in the boiler subassembly in the same way that we assign the frame sketch. Assemblies typically contain common parts, and we call these instances, and fast duplication of virtual components only require that we determine their position in the assembly. Think of the power here. One simple rectangle and its node in the tree quickly became several parts. Using a keystroke, we can easily rotate the block into the position that we desire. The bill of materials will automatically sum the counts for us. Some immediate advantages of this process allows us to show and hide component sketches by setting the visibility in the virtual component, a familiar process found with actual 3D parts. Here we'll create a circle to represent the pump. Once we assign that sketch to the virtual component, again we'll show you the power by duplicating that instance. You can easily see the power of taking 2D layout and assigning it to virtual components in the tree. This similar process also works with existing 3D data. Remember that when we created the assembly tree using virtual components, we added 2 real components. Those are now listed in the assembly tree, and we just need to tell Solid Edge where they go. A simple drag and drop will place the conveyor turntable into the assembly, and again, using model key points, the correct fit and position are guaranteed. Let's see this process again with another virtual but real component. Notice the components look like 2D sketches, but we said they're real 3D parts. The parts are 3D, but we used a 2D sketch to simplify its representation. This provides a huge benefit in terms of performance and manipulating the design. Later in the process, when we're ready to commit to this project, we'll publish the virtual components and where all the nodes will become actual files on disk. The 2D sketches will also come to life with actual 3D models. It's really quite impressive. Our 0D workflow enables us to mix and match data types so we can maximize reuse and take full advantage of existing 2D layouts. So far we've used virtual components based on 2D sketch elements. We've added virtual real parts, which are 3D components but in a simplified 2D form. So now let's complete the story and add some 3D models. Notice that we're in the sketching environment, but we still can place 3D components and position them to the layout. This capability allows us to properly position 3D components from the 2D perspective, and it's done in one simple environment. We can choose to move the 3D assembly to the sketch or vice versa. In this case, we'll make the sketch drive the position of the 3D component. Positioning 3D parts in this manner gives you ultimate position control given a 2D view. We could position the assembly relative to the front view, but this is a plan view layout, so now we'll just set the machinery directly on the shop floor. Think of our 0D workflow as a digital sketch pad. We simply sketch the outline and position of the major components, and at any time we can modify their location and add or remove content at will. When we're sure the design is ready for the engineering team to complete, we simply need to save the virtual components to the actual files. This last step is where we will publish the design. Because of the fluid approach to the assembly development, we didn't need to worry about where the data was. But now we're going to create physical files, so let's set a path to our project folder so the newly created documents will be placed there. Any actual 3D parts that we added will remain in their respective folders. For example, our part libraries will still contain all of our common data. Also notice the intelligence of the system by using simplified representations. Large assemblies such as plants and equipment consume resources, and this option will help retain as much computing power as possible. Notice the tree now lists physical documents and in the exact structure as our virtual assembly. Remember, we quickly built the structure with virtual components, and now our production assembly is accurate and organized. A more obvious change is what happened to the layout. Notice that the layout is still there, but take a close look at what happened to the 2D components. These virtual components have been replaced by actual 3D components. It's easy to see the performance gains with 0D. Users can build massive assemblies centered on a 2D layout and have an accurate representation of the shop floor during planning. Only when the design is ready for details do you need 3D. Let's continue with 3D work. In this next step, we'll drag in an OEM part into the assembly and position it relative to the assembly sketch. As part of our process, any OEM data received should contain a simplified representation of the part or assembly. This process is quite simple but yields some drastic performance increases. Remember that squeezing every drop of performance from our system is important when dealing with massive assembly designs. Typically, we would think to add components directly to the others, but in the early phases of plant layouts, these parts may not be ready. Solid Edge allows us to easily place 3D components directly to the 2D sketch. Since the layout defined the spatial location, why not have that same layout drive any changes? We call this a hybrid approach to the assembly design. A quick dimensional change of the layout sketch shows the 2D elements can set the position of the newly added vendor assembly. The larger assembly, the more common having familiar parts becomes. The number of conveyor sections in this assembly is a perfect example of this. While we can pattern and place these components to replicate them in other areas, a natural workflow would be to just take one of these and put it over there. The component move command in Solid Edge has an option to move a component while making a copy of that part or subassembly. Here we're going to simply copy a small conveyor section to a new location. Next, we'll rotate the conveyor into the position so it's in the correct orientation. We'll see other uses of this command and how it's an extension of patterning later on in the demonstration. This precision table seems to lack precision, but remember it was placed in a simplified state. We can toggle the display to show it in its fully designed form. Solid Edge was designed and architected for performance, and having the ability to switch between fast or accurate representation of parts and assemblies is key to large assembly design. Notice that Solid Edge simply turns off the edges of the parts during rotations for faster display. This is just another proof point of Solid Edge's commitment to performance optimization by adjusting the display to maximize performance while retaining as much detail as possible. Let's design the boiler next. If you'll remember, we created a 2D sketch representation of the boiler earlier in the demo. When we published the assembly design, the sketched elements were copied to individual files to which they were assigned. We could of course design all these components from the sketches, but since this model exists, we'll simply replace it. We use the sketch during the concept or layout phase to determine its location, and then we will replace it with the actual 3D model when it's designed or supplied. Remember that this virtual component was published to a 3D model file, so replacement is a simple process. The new design drops into place exactly where it should be. So now we've begun to see how productive Solid Edge is for plant layouts. Solid Edge's unique 0D workflow for creating and working with 2D layouts during a conceptual and planning phase provides a smooth transition into full production design. While this demonstration is centered around plant equipment and layout, the tools and methods in Solid Edge scales to an assembly design. Some key tools and an optimized architecture make Solid Edge the best solution for the assembly design. Assigning designers to tackle plant designs can be done from a file standpoint, where a particular engineer manages a particular subassembly and so on. Zones in Solid Edge takes management to another level. While most systems are organized in separate assemblies, it's often important to know what other systems interact with it.